I am very gratified to announce today that we have reached really the last major milestone on the long construction process for this bridge until we open it to traffic less than a year away now in Labor Day 2013. And that milestone is what's called load transfer. One of the unusual design features of this new bridge is, of course, the steel portion at the deep water near Yerba Buena Island, where the bridge is a self-anchored suspension span. And unlike a traditional suspension bridge, which has earth anchorages at either end, and that's true of the west span of the Bay Bridge, as well as the Golden Gate here, as well as the new Carquinez Bridge that we built just a few years ago, our bridge does not have earth anchors. It anchors into itself. Since this is a self-anchored bridge, and it essentially holds itself up, until we completed that engineering mechanism, the bridge needed to be supported on temporary falsework. And that temporary falsework is quite visible today. We've started, as part of this operation, to remove some of that falsework, because what's happened over the last few months is the deck has been connected by those suspender ropes that you see out on the span. The bridge has been attached to the cable, the main cable, and the main cable on our bridge functions just like the main cable on a typical suspension bridge. It holds up the decks. And so what we've completed today is the culmination of all of the work, all the design effort, and now the bridge is supporting itself, and it is functioning as a suspension bridge. So that is the milestone we announced today.
The next thing we want to do is just run you quickly through what the job was like. Okay, hit it, Paul. So we're talking about the main cable of the bridge, the suspender ropes that come down from that, hydraulic jacks really did the heavy lifting for us, and the temporary supports. Now what you'll see in these animations, though, is just the concept. The crews, there were 8 of them for American Bridge Floor that were out there, were really the people working late hours in sometimes difficult conditions to get this job done. Okay, go ahead, Paul. So basically what we're doing is this temporary work. We had to build 2 bridges in order to get this bridge was placed. The decks were set on top of that, on top of these cradles here. And then what we're doing is we're transferring the load onto the suspension system, which you see here. In order to do that, the jacks are going to be pulling down on this cable. But what is a self-anchored suspension bridge? I think Steve explained it pretty well. Here's a graphic that helps out a little bit. Ours is unique. We're building the world's largest self-anchored suspension bridge, and the only one with 1 central tower and only 1 main cable. Instead of having 2, or some people even think there's 4 out there, this main cable anchors on the eastern side of the bridge, goes up to the top, across traffic, crosses traffic again as it loops right around the back end here, then continues over traffic up to the top of the tower and anchors on the eastern side. Some of the key areas for our bridge on the east and the west, the splay chamber right here. This is where our cable comes back and ties inside the deck. It fans out, and each one of those strands, there are 137 strands in the main cable. Each one of those strands has 127 5mm diameter wires. They're all locking back into a very sleek anchor point right here. The other unique thing about this bridge is that it wraps around the back end here, and we have a jacking saddle, which you'll see a little bit more of, that places tension on it after at the end of load transfer. Again, how do you build a self-anchored suspension bridge? Now that we know what one is, some of the key components so you can see how important this operation was. First, you put the temporary works up so that you can get ready to receive the decks. Then you construct the decks. As Steve said, there are 14 on each side, so there are 28 total deck sections that are out there. And then at the same time, we built the main tower, 525 feet tall, 4 independent shafts. Now that we have that in place, the cable system can be constructed. We place the main cable out on the bay, and you can see here that it does not go down into the ground. It wraps around there, locks in there, no touchy. Then cable bands are placed on the cable. These things act like saddles so that we can place the suspender ropes that radiate straight down at an angle for us on this bridge because this cable is crossing, and connect into the deck and ultimately lift it up. And at that point, you can begin load transfer, lifting the deck off of this false work and putting it onto the main cable. Then once those and a few other steps are done and we know that we are ready, we can remove all of the temporary works. Some of the temporary works we've already started removing. So we're going to show you the simulation, and please keep in mind that this was not a linear process. These things all had to happen at the same time. So we had 8 crews out there doing this work. Caltrans engineers stood right alongside the engineers from the contractor. T.Y. Lin, Moffitt Nickel were the designers of record, and we'll go into what the process was. Okay, there's the support system, the temporary works. This had to be done in 3 different phases. The first phase was to connect 104 cables. They would be pulling on the main cable. It deforms a little bit into its final geometry. Second phase, the suspenders near the tower. Third phase, distributing the weight on the remaining 96 strands, suspender ropes. And then this is the system that's holding up the bridge after load transfer. So here are the 6 key areas of load transfer. So we start with, watch the main cable here. It actually moved 30 feet down, 16 feet out. It's about 5,000 tons of steel there, 35,200 tons of steel down here. Massive lift, the largest on our project. And here's a little bit of what the site looked like. You can see all these platforms that were constructed above the bay. You can see the ironworking team that was out there with our engineers at each one of these different locations. Okay, now we're going to go back in time. We're going to look at this again. The jacking unit right here is actually pulling down on the strands that are connected at this point. You can see that the cable's deforming up there as we're trying to get these pieces down into this anchor point where the suspenders actually connect onto the deck of the bridge itself. And again, these animations, they don't show the humans that were out there actually doing this. So then you can place the hardware on, nuts and bolts. You want simple forms, simple construction hardware when you're dealing with something this big. Now here is the team doing it. Actually out there in the field above the bay. You see the cars down there? While the jacking is happening, you can see the nuts that they're placing by hand at these different locations. Well, the whole point here is to get separation, to actually lift the bridge. This is exaggerated a little bit to really take home the point that we're lifting off of these cradles and this temporary bridge and putting the weight onto the cable system itself. And then the cradles are then removed. As you'll see in the construction footage here, we've already started removing some of the cradles closer to the eastern side of the bridge. See, they are gone. You can also see the separation at this location and that the bridge is holding itself up now. Well, the bridge started moving in many different locations, so key components we couldn't lock down because we knew the deck would still be moving as we loaded it. So here where we have bearings that allow the bridge to move and shear keys that hold it down in certain directions, we did not lock them down so that the bridge could get into its final geometry. In an earthquake, we need that bridge to move. So here is one of the large-scale bearings at that location and how much movement it could potentially accommodate in an earthquake. Moving on. So now we're at the back end of the bridge, and we need the tension to be correct on this part of the cable that's coming around the back end. So we created a jacking saddle here. We have hydraulic jacks pushing against the saddle, and then steel plates put on the inside of that to get the spacing correct, so we know we have the right tension on the back end of the bridge. Once we have surveyed it, we know that the stresses are correct. We fill the cavity with the rebar. We grout it with concrete, and this never moves again. So a couple of quick shots of that area. There's the back end of the jacking saddle. You can see the cable coming across. Here's the space in between the bridge and the cable right there. There's the jacking saddle. And on the inside, Paul, if you can hold that for a second so you guys can get this. Here we have the steel plates. They're stacked up right there. The hydraulic jacks pushing against the saddle right there, and they're put in like spacers until we get that correct. Okay, so that is the jacking saddle. And then we actually had to pull the main tower out of plumb. So as we weighted it, it came back up perpendicular, and these steel strands that we connected to the top of the tower and anchored down at Yerba Buena Island were slacked. We had pulled the tower out of plumb a few inches, and then as the weight was put on, we allowed the tower to go back in. So here you can see cable strands that were coming down from the tower, connecting down to the island. This is what it looked like on top of the tower, how they were secured to the tower top. Here they are slacked after we've released them. Now, the main parts of load transfer complete, we can start putting the hardware where it needs to go on the bridge. So you can see these elements are the next ones that we'll be placing on the back end. And then we've got it. So those are the key portions of load transfer. Paul, can you hold it for 1 second? This is what we're doing now, along with some painting, as we're trying to knock off that really long punch list so we can be ready for the opening in Labor Day 2013. We are wire wrapping the outside of the cable. So how do we protect that main cable from corrosion? Well, we start off with the individual wires are all galvanized. Then on top of that, you can't see it right here, but we use a zinc-based paste that we sort of slather onto the main cable so that we've got that tight connection. It almost forms like a gasket. It's so thick on the outside of the wire. So that's 2 levels. The next level we do is this S-wire wrap. It actually interlocks. So go ahead and roll it, Paul. As we wrap radially around the outside, it'll go the right direction, of the cable so that you have a tight lock. There's the zinc-based paste. Then a 3-coat paint process on the outside of that should get us over a century's worth of life out of this main cable. Bay to bay, we have to skip, obviously, where we have the suspender rope saddles. So that's what we're working on right now. Now the bridge has stopped moving at this point, so we're also working on lining up the different decks. This is the Skyway portion of the bridge. This is the SAS. There's jacks out there right now where we're exaggerating again how perfect this will be, but we have to get this connected in such a way that you don't feel a bump when you go across these different bridges. So these jacking platforms and strand jacks here are in place right now. Then one of the innovations on this bridge, the hinge pipe beams that protect us in an earthquake, will be slid from the Skyway into the self-anchored suspension bridge, locked down on the SAS side, and they can move on the side that the Skyway's on. We have a fuse in the middle of them that can bend and contort in a massive level earthquake. And then right here, this area of the hinge or joint, actually you get an accordion, steel accordion plate that goes down there that allows the traffic to, or steel plates in this case, that allows the traffic to go across. Then other hardware can be placed. Again, the bridge is not moving any longer so that we can start really locking it down, getting the cowlings on the key areas that we need them. And down here, we can return to this part of the bridge where we have the bearings and shear keys and actually pin them in. Put the steel rods through this bent cap right here at what we call E2, lock them down with our very simple nuts and washers, and get the rest of the material in place, and then grout them, concrete them so that they do not move over our century of use. Once we have that, we can remove the false work, and we're done on that side. Then we can begin removing the false work. The tower first, we'll work our way down to the substructure, and we'll have the world's largest and most beautiful self-anchored suspension bridge right here in the Bay Area. Again, all of these assets are on BayBridgeInfo.org, 2013, Labor Day weekend.
What I would liken it to is we're unwrapping a present. We're unwrapping a gift, and we're certainly very pleased with the milestone that we've reached today. And we can smell the finish line now, and we are going to put the pedal to the metal and get this new bridge open to traffic as quickly as we possibly can next year.